ch14, chapter 14 continued. This is section 4, average power and the power factor. So the formulas of note, if you want to find the average power, you could take the maximum voltage and current divided by 2 and multiply it times the cosine of the angle in between the V and I waveforms. This theta is the phase angle between V and I waveforms in degrees, and the way that you calculate is you take the theta V minus the theta I and take the absolute value. You could actually flip these around and it'll still be the same thing. If you take theta I minus theta V and take the absolute value, it'll still end up being the same number. Theta V is going to be the in the voltage waveform, whatever the phase shift is given, and theta I is the phase shift in the current waveform. Another formula, which is basically the same formula, is V RMS times I RMS times the cosine of theta, where V RMS is the RMS voltage value in volts. I RMS is the RMS current value in amps. Question is, what is the RMS value? The RMS value is the root of the mean of the square. So what you're doing is you have your waveform. So here's a graphical depiction of a voltage waveform, okay? And they're using V sub pk or peak to show you the peak value. What I was saying, V sub n for the max value, it's the same thing. That's the amplitude of this signal, okay? And then VPP is the peak-to-peak voltage, which is just, it's typically if there is no DC component and we're on the average value is 0 as shown on this graph, and the peak-to-peak voltage is just the like 2 times this number. So if this was, say, like 3 volts, then the peak-to-peak voltage would be 6 volts. Okay, because the positive peak is +3, the negative peak is -3, and the total distance between the two is 6. The RMS value is a calculation that's done on all the points in the waveform. So like I said, you take the square of all these points, and what ends up going to happen is the negative values get flipped up, and this looks like a bunch of mountains, like it's a bunch of humps going this way. And then you take the mean, the average of all those values, and then you take the square root of that number, and what you end up with is a number like this, which is it's the peak voltage divided by the square root of 2. Okay, so whatever this number is, and this same thing goes for the current. It's not just with the voltage. So the RMS value is this V sub m divided by the square root of 2. So just remember, V sub m is the VAX value. It's always bigger than the RMS value. So the peak voltage is also equal to the square root of 2 times the RMS. So here's the formula for, say, V sub m. V sub m equals square root of 2 times V RMS. And then that goes the same thing for I sub m. I sub m would also be the square root of 2 times I RMS. So to calculate the power in a circuit, you would take V sub m times I sub m divided by 2, or take the VRMS times the IRMS. That'll give you the real power. And if it's a truly just a resistive circuit, the you can also calculate by using VRMS squared divided by R, or IRMS squared times R. And the average values in watts. And In a purely capacitive or inductive circuit, the power dissipated by the element is zero, meaning neither one of these elements dissipates real power because they are a reactive element. They only have a reactive component. The power factor, symbolized by PF, is equal to cosine of theta, where again theta is defined by this with this formula, and it's also equal to the average power divided by VRMS times IRMS. Capacitive networks have leading power factors. The current leads the voltage across a load. So theta sub I, the value of theta sub I, is greater than theta sub V. And then inductive networks have a lagging power factors. The current lags the voltage across the load. So theta sub I is less than theta sub V. We're going to be using complex numbers to represent those elements and represent the voltages and currents through them and across them. The complex number is a point in the 2D plane with a real axis and imaginary j-axis, also called the phasor domain. This is what it looks like here. So your horizontal axis is your real axis. This is the plus side, this is the negative side. And then the imaginary j-axis, this is the plus side and this is the negative side. The rectangular form of complex number, C equals X plus J Y, where X and Y can be any value on the real, X is any value on the real horizontal axis. It's any number. It's not just an integer and it's not just a positive number. It could be a negative number. For our purposes, this is going to end up being the resistive component, and it's always going to be positive. But for complex number general math, it can be negative, and then the y value is on the imaginary vertical axis, and again, it can be any number along this line that could be positive or negative. The value of z of the polar form, this is the rectangular form, this is the polar form, so z equals the angle of theta, where z is the magnitude value of the vector, the phasor, the hypotenuse. So it would look like this. This is what it looks like. And then this is the phase angle of the phasor, and it's always in the degrees that we use it for. And then to convert between the two forms, it just use Pythagorean theorem. Z equals the square root of x squared plus y squared. And then theta equals the inverse tangent of y over x. That's trigonometry. And then when you want to convert from polar to rectangular, x equals z times cosine of theta, and y equals z times sine of theta.